again, or your password is not right, try again.
That's why they use using password is invalid.
Right. So instead of telling explicitly your password is not right, the error message that most of the time you get what? Either username or password is not correct, or wrong information, invalid information, or something like that, right? So you have to be very careful from a design point of view that you don't tell the error messages very detailed enough so that you give out all the information, right? And so that's one example of failing securely, which means even if a system fails to function because of some user activity, it has to fail to a state which is secure enough, that's not being exploited. Even ATM machine, if you're trying to detect, take some money from the ATM machine, if you didn't enter the right PIN number or something, right, it should fail back to a secure state so that the money is not withdrawn from that user's account which you're trying to get the money from. Okay? Now, least privilege. Least privilege is like, the same thing as I told before. The user should always get the lowest privilege, okay, to access something. So for example, if I can register as a course, say let's say you go to the dean of the school and ask him to register you for a course. He should be able to register you for a course as a faculty level user. So even though as a dean he can register you for a course, at the time of login, if that's a role-based access. So the system should determine what is the role he's going to take. He's going to register you for the course. So the system should provide him only the lowest level of access he needs to register you for the course. Even though he can register you as for the course at different levels, right? You should be given the least privilege needed to do that thing, so that a user doesn't exploit the higher levels of privileges given unnecessarily. Okay? So that's what is meant by least privilege. Separation of privilege. This goes with, actually you should not decide to do certain things based on just one permission. So always you should have multiple conditions that need to become true before you let a user to do certain things. Even in day-to-day life, if you have had what you call safety lockers in banks, sometimes they have two keys for the lockers. The customer will have one key and the bank will have the other key. So the locker cannot be opened just with one of those two keys. Both keys have to be used to open the locker. So which means if even one key goes to the hand of an attacker, he cannot come back and open the locker. Both keys have to be there, right? So same way, in an application, you should never let just one condition to become true and let something to be executed. You should always have multiple conditions to become true. Even from a login point of view, I think we covered this in the login chapter. You have multiple levels of authorization. Have password-based thing, have biometric-based thing, have smart card-based thing. Even the smart card, I told people swipe the card and type a PIN number, right? So even if the smart card gets lost, they have to know the PIN number to enter the room, right? So that's like 2 or 3 factors of authentication, not just one factor for authentication. So always have separation of privilege in your application design, so that it's just one condition, someone cannot penetrate your application. Reluctance to trust. Reluctance to trust means, for example, sometimes when you write your code for application, you spend most of the time in testing the user inputs, like you did the equivalence class partitioning and all those things, right? So you tested if the user enters a negative number or a positive number or a fraction or whatever, right? Because you think a user may try to cheat and enter wrong information. But if the input for a program comes from a file or comes from the network from somewhere else, an application design developer normally trusts that source. He thinks whatever read from a file is more trustable compared to input coming from a user. But as a good design principle, you should not trust any input source. So you should subject the inputs coming from a file to the same rigor of testing that you subject an input coming from a regular user. Because let's say if you trust an input coming in from a file, an attacker figures that out and puts all the garbage or whatever the input that he wants by kind of trying to managing to get access to that file. Then the application reads that file and it behaves arbitrarily. You don't want that to happen. So never trust any source of, for your input for your application. Always subject them to go through some testing. Okay? So even posts. So even though, as I said before, some posts trust the other posts in the network so that they don't go through the authentication procedure all the time. It's not a good design practice, because once one machine is infected, the other machine can be easily penetrated. So never trust anything that easily. Okay? And never assume the secrets are safe. Some people hard code their passwords. For example, if you're designing a database application, you hard code in your application, this is the password that needs to be used to access the database. And you think the original source code will not be available to the attacker, only executable is going to be available. But I think I told you before, you can do what's called reverse engineering, right? There are what is called programs called disassemblers. So if I give you an exe file, I can get the original C++ or C code or Java code. If I use a class file, I can get you can get the Java code. And there all your secrets will be there. So never let any password or anything which is hard coded in your program. Always store them somewhere, try to read from the database or wherever you're storing it in a secure fashion, and then check whether the user entered the right password or whatever. Okay? So never hard code your program. And do not cache access control decisions. We saw that several times in this course, right? The top-down attack is an example. You cache the kind of the file reader basically once you open the file, and after the file reader is declared, you try to remove the access for the other user, but still you're able to continue to read the file, right? That's because of this caching, because you check the user has permissions at the time you open the file pointer, and then you use that cached information to let him to read the file or update the file. But his access has been removed by it. But the system, the program doesn't check that, right? But then again, only when you really again go back and check whether he has access or not, you are able to capture it, right? So it's always not a good strategy to cache your decisions. But it's a trade-off, because if you want that particular top-down program that you develop to check for permissions, what will happen? You slow down your program, right? You have to check every time you want to do a write. Okay, so that's the main reason people do certain things like this. They cache the access control decision because they want some real-time performance. If you want to check every time you want to update a file, whether the user who has the access to the file or not, it will take a lot of time, right? So there are certain trade-offs. So you cannot really achieve, even between these principles, you cannot achieve all of them together. There are always some trade-offs. But this is something that you should know or practice, put into practice when you start designing software. Okay, so these are some of the principles for secure software design. So if you take a software engineering course, you may see something more or something different. But from a security point of view, these are some of the principles. Okay? Alright, so start with this end of this course.